Welcome back. We have been talking about the synthesis of polyamide in some detail, and we continue to talk about that. In the last class, the point where we left you is we were looking at the details of the polyamic acid synthesis, why we are using low temperature, why we are using a certain kind of solvent, say polar aprotic solvent, why you are using one reactant as a solid form, in this case dianhydride, and adding gradually to a solution of your diamine, why that gives you a high yield of polyamic acid, why at all go through polyamic acid and do not go directly to the polyimide, those things we have discussed. So, let us continue talking more about polyimides. So, let us say we will talk about one commercially important polyimide first up today. So, that is Kapton. So, basically if you start with your pyromellitic dianhydride, react this with a diamine which has an ether linkage, a specific diamine we are using this case. So, basically this is a di 4-amino phenyl ether. So, an ether linkage, and it is 1, 2, 3, 4. So, this is 4-amino phenyl and there are 2 of them. So, this is di 4-amino phenyl ether, and this is a 2-step reaction. Of course, you go through the polyamic acid synthesis, and what will be your product? Your product will be, after going through the polyamic acid pathway, of course, you will get your polyimide which is of this form, oxygen, and then you have this. Okay. So, this is your R group. So, this is NR like this. This is the trade name of this particular polymer is Kapton. Do not get confused between this circle and this circle. This is your aromatic ring and this is your oxygen. Okay. So, this particular Kapton, this particular material, the Kapton, when you make a film out of this polyimide film is basically stable across a wide range of temperature from minus 269 degrees Celsius to plus 400 degrees Celsius. And because of this kind of exceptional stability of this material, this is especially used in some highly demanding applications, say for example, as thermal blankets on spacecrafts, satellites, etc. And they have very high, I mean they are very costly. In spite of their high price, because of their exceptional heat resistance and good properties at high temperature, we can use in such demanding applications. And in fact, the reactant, say for example, we are talking about this pyromellitic dianhydride, but we did not tell how it is prepared. This reactant, although it is quite costly, it is still readily available. How do you prepare this material? So, you start with, of course, the corresponding methyl substituted benzene. This is basically called, this has a name, it is diurine, and you oxidize with nitric acid. So, liquid phase oxidation reaction, and you get your pyromellitic acid, as simple as that. And this pyromellitic acid, if you heat it up, you will cyclize and you get your pyromellitic dianhydride. Okay. Now, when we are looking at commercial polyimides are not always prepared from a simple diamine and a dianhydride, because if you just look at these polyimides that we talked about, I mean I am not talking about Kapton, because Kapton is slightly different, it has already an ether linkage here. I am talking about just a diamine which does not have any other linkage, say benzene ring NH2 NH2, and you are reacting with a dianhydride, so on and so forth. So, in those kind of situations, polyimides that we are making, although you can go through polyamic acid and all, but it does not change the fact that ultimately the final product that you have, the applications are quite limited because they are infusible, they cannot be molded by conventional thermoplastic technique. Because even though you have made the polyamic acid and you have removed the solvent and you get the shape, you cannot mold them by conventional thermoplastic techniques, because now if you heat it up, they do not melt, they do not simply melt. If you can introduce some thermoplastic property, for example, a little bit flexibility at high temperature, that will help. So, commercially modified polyimides are used. I mean, lot of modified polyimides are there, modification of polymer structure has been done. So, some of the important things, for example, they are polyetherimides or polyamide-imides or polyester-imides or Bismaleimides, which have better property than your conventional polyimides. Let us say polyetherimides, so just abbreviation as PEI. These typically are high temperature amorphous thermoplastics. Because they have not only repeating imide linkages, which helps them to have high temperature stability, I mean the material property can be retained, but not only that, but they are also thermoplastic materials because they have regular repeating ether units in the system. So, the imide units, they provide stiffness to the material, and the ether linkages, they will provide the flexibility to the material. So, that will allow good melt flow characteristics of the material. So, the processability, the process in the processability, it becomes easier, the processability becomes easier, say injection molding or likewise extrusion, those kind of things can be done. Now, one example is Ultem, which is a commercially available polyether-imide, and this basically is prepared by this process. You start with this compound. So, this is a sodium salt of bisphenol A. So, this is sodium salt of bisphenol A. So, basically bisphenol A is this, this is bisphenol A. Now, bisphenol, you know there are two phenol units. Why it is A? Basically it is produced by the reaction of acetone CH3C double bond oxygen CH3 by the reaction of acetone with phenol, and that is why this is called bisphenol A. So, and it could be bisphenol F, for example, in that case it will be reaction with formaldehyde. Okay. So, bisphenol A, sodium salt of that, and you react with this particular molecule. So, this is meta substituted molecule. You have already have an imide linkage here. This is aromatic ring. On this meta position you have the same stuff that is here, another aromatic ring, and you have an NO2 unit. And if you react these two molecules, sodium nitrite will go, and the final product that you will have is this. So, basically I am just drawing this part first. So, your imide linkage was already there to start with, and so this was this part, and then this in here this oxygen will be linked. So, you have oxygen and then you have the bisphenol A part, this is your and here you had this NO2. So, here will be the linkage. So, this is your Ultem. So, this particular starting material can be obtained quite easily starting from phthalic anhydride. So, basically what you do is you start with phthalic anhydride. So, this is this is a phthalimide unit, because if you have a CO2H here, a CO2H here and only benzene ring, that is called phthalic acid. So, you start with a phthalic anhydride, okay, and you oxidize this. Basically, you react with nitric acid, you nitration, you nitrate this particular molecule. So, what we will have is 2 position and 3 position, either 2 position or 3 position nitro group will be coming. That is why I am just putting like this, the nitro. So, this is basically nitrophthalic anhydride, nitro. So, this is your nitrophthalic anhydride, okay, and then that you react with metaphenylene diamine. So, this is metaphenylene diamine, this molecule has made its appearance before, and then what you get is your Bismaleimide monomer, okay. So, your this nitrogen will come here. So, it is producing imide in the place of anhydride. So, basically it will be like this, and your nitro group is here. So, this part is on this side, because here this can produce the imide linkage, okay. It produces the amide and then it can cyclize by removing the water, and you will get the imide linkage here. The same way on this side also you can get the imide linkage. The structures sometimes might look complicated, but as long as you are following the logic, it is not that difficult, and this is the starting material of this, that you can react with the bisphenol, sodium bisphenolate salt, and then sodium nitrite is evolved, and you get what you call, the commercial name is Ultem. So, basically in this step you are using a base in order to make it O minus, and you can use again say a solvent which is polar aprotic solvent, and you have to reflux this reaction and you get your product. Now, something that I need to tell you here. So, this particular product, it is an amorphous product, it has all these ether linkages here, and the temperature at which you can use are around 170 to 180 degrees Celsius. So, still you can use at quite a high temperature, and the solvent and chemical resistance are basically comparable to that of polyimides. One thing that you have to keep in mind here, when you are going to the second stage of the polyimide preparation, in the typical polyimide preparation process, say for example, this process, here you are going through polyamic acid synthesis. So, when you heat this up and you get your polyimide, you are basically producing water, because this is cyclizing. So, you are basically producing water which is volatile and which is going out, and that can lead to the presence of voids or strains in the product during the processing period. So, basically when you are going through polyamic acid, ultimately you are heating it up further once you have molded the material into the shape you want, and then the polyimide is being produced. This is releasing water from here, and that is why the cyclization is occurring. So, that would mean the water has to go out. So, the material, some voids, some strains can be remaining, because it is a volatile product that is going out, and that kind of defect can be there, and those defects will not be there, or those kind of problems will not be there in this particular process, because this does not involve production of any volatile component in this polyether preparation. So, this is also advantageous process. Okay. Now, this is an example of polyether imide. An example of polyamide-imide also I want to give you. So, you can simply start with, again you need an anhydride and the reaction with a diamine in order to produce your imide linkage. Now, instead of another anhydride here, which will be pyromellitic dianhydride, you can have a CO2H here. This is basically when you have a CO2H, 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 it is pyromellitic acid. When you have a CO2H, CO2H, CO2H in these 3 positions only, that is trimellitic acid. So, if you have this anhydride here, this is called trimellitic anhydride. Okay. Now, if you react here after removal of water, it will react and then it will cyclize removing the water. The product that you will get is something like this. Now, it should be easier for you to draw the product. The imide linkage will be produced on this side, and on this side you have carboxylic acid that will react with this amine to produce amide linkage. That is why you will have polyamide-imide. Okay. So, the product here will be something like this. So, this is your polyamide-imide. This also will have high strength, high stiffness, and these are amorphous polymers, and the continuous use temperature is around 220 to 230 degrees Celsius. So, these do not fare too badly with respect to your typical polyimides, I mean conventional polyimides, but these are easier to handle some of these materials. Now, finally, what I want to talk about in this particular, okay, let us also talk about one or two uses of these kind of materials. So, they are used in aircraft, jet engines. I mean, when you see some of the uses, it is important to try to rationalize on the basis of structures, high temperature stability, and say for example, Kapton you are using in spacecrafts, there can be huge temperature fluctuations and all. So, those things, because it can withstand these kind of huge temperature fluctuations and still can maintain its mechanical strength. So, those kind of things will tell you why an application, I mean, can be envisaged from such materials depending on the structures. That is why understanding the structure is very important. Correlation with properties comes after, and designing of the structures so as to obtain the polymer property that you want comes even after that. So, it is used for aircraft, jet engines or in other industrial applications like in machine gears and other mechanical components, so on and so forth. Okay. So, let us talk about another class of polyimides now, I mean commercially modified polyimides. Already we talked about polyamide-imide, polyether-imide. Ultem is one of the polyether-imides. So, Ultem, we talked about Ultem. Now, let us talk about another kind of imides, another class of imides, which is called Bismaleimides. I will explain to you why it is called maleimides, polybismaleimides, etc. So, of course, this is polybismaleimide means you have to start with bismaleimide monomer, whatever it is, I will come to that in a moment. So, maleimide, basically this means an imide starting from maleic acid, like pyromellitimide, that means an imide starting from pyromellitic acid. This is how you can link the things. So, your maleic acid is this is your maleic acid. What you do in this case is you start with, now you can understand this is maleic anhydride. You react an anhydride with a diamine, and what you will get? You will get an amide linkage here, and this will open up and produce the carboxylic acid, and then if you heat it up you will get an imide linkage. So, if you are reacting an anhydride with an amine you will get an imide after. First step you can get an amide linkage and a carboxylic acid, and then when you heat it up they will come together to cyclize, remove the water and it will form the imide. So, what you will get is this compound. So, sorry, so CO NH R NH CO CO2H CO2H. Okay. So, two of these molecules come together from both sides and this opens up because this will attack here and this will open up. Okay. So, you will get this compound, and then when you heat this up water molecules will be removed from this side and from this side, and you will get the cyclization and the corresponding production of imide. So, this will be your imide, and this imide is produced from maleic acid. So, that is maleimide, and there are two of them, that is why this is your Bismaleimide. This is your starting material. So, you are reacting maleic anhydride with a diamine and you get your Bismaleimide. Now, what you do is that, so this is BMI, Bismaleimide. So, this Bismaleimide, you react this Bismaleimide with say another diamine, that is why I am putting R prime. Now, since it has two functions here and this amine has two functions on both sides. So, basically it can form a polymer because this amine can attack here on this double bond. So, what will happen is that the product that you will get is a polymer which looks something like this. So, the basic skeleton is this, okay. And then instead of double bond you are actually reacting with this diamine. So, you will have the diamine on both sides. In this case here you are removing the R or R prime, that R prime then should come on this side, it will be NH R prime. Remember, you should be able to draw the repeat unit in a correct fashion. If you do not put R prime here, you can put R prime here, still the repeat unit is correct, okay, because you have to account for both of the molecules, they will come into the repeat unit. So, like this. So, this is your polybismaleimide. Now, let us say you carry out this polymerization with an excess of bismaleimide, then what will happen? From our previous discussion on step polymerizations, we know if you have an excess of one of the molecules, that will end cap on both sides with the same functions. So, if you are using an excess of bismaleimide, then in effect the product will have, so this is a polybismaleimide unit, and on both sides you will have these maleimide linkages at the end, because this is in excess. So, both sides they will end cap. So, ultimately the product that you will get, the polymers that you will get, they will be, so this is the polymer, I am just not drawing the structure here in between, they will be end capped with this maleimide units, because the bismaleimide has been used in excess. So, this is maleimide end capped polymer. Now, here these terminal double bonds, they are reactive double bonds. These double bonds can be further used, they can actually serve as what you call as Kehr sites for the formation of cross linked material. You know, this kind of material, when you do what you call as a Kehring, you basically add a cross linker that will cross link the material and it will produce what you call as a thermoset material. A 3-dimensional cross link material will be produced, and many times it so happens that you have a cross linker, you have a functional group at the end, in this case maleimide end group. This reaction is done at a higher temperature. So, basically you have to heat it up a little bit, you put a cross linker, you have your starting material which is a reactive functional end and it cross links, and then ultimately you get a material which is stable material, which has a cross-linked structure, covalent cross-linked structure, and it is a thermoset material because you have set it into a particular structure by heating, and it is also a curing process, and the curing agent being the cross-linker. So, once you have cross-linked, you get the thermoset product, which is unlike your thermoplastic material, because thermoplastic materials, when you heat them up, they become malleable, they become pliable, they become softer. You heat them up beyond their glass transition temperature, they become softer, and then if you cool them down, so you heat it up, you reshape it, you cool it down, it takes whatever shape you want. Okay. So, that kind of thing is not possible when you are talking about thermosets, because you basically are adding a cross linker and then you are heating it up. So, it is actually setting the material into that particular structure, which is covalently linked structure. Now, the only way you can do something is to break those bonds. So, you can destroy the material. So, it is not like you heat it up, you can reprocess it. So, that is a thermoset material. So, here, so you have this kind of double bonds on both sides. So, you can do a cross linking, okay, and you can get thermoset products which will have this kind of structures. So, you have cross linking like this here, nitrogen, and let us say, so this was the actual polymer to start with, okay, and then so on and so forth. So, this kind of cross linked materials, this kind of thermosets you can produce, and the properties of this kind of cured polymers will be broadly similar to the polyimides that we have talked about, and the continuous use temperatures could be still as high as 200 degrees Celsius. So, you know, again this can also be applied in aircrafts, spacecrafts, and other kind of highly advanced applications. So, finally, what I want to talk about is the following, that basically, I mean, since we are talking about these thermoset materials and we talked about these Bismaleimide units. So, we have already talked about a process in which you can create thermoset materials. So, basically there is a name for the approach. It is called reactive telecalic. I mean, of course, whatever we have talked about, it is different from this. I mean, I am just trying to correlate in a way that we talked about thermosets, we talked about malimides. So, we are talking about another approach in which you can use these malimides in order to create thermoset materials. So, reactive telecalic oligomer approach. So, in this approach, what you basically do is that when you are polymerizing your system, you include a monofunctional reactant in the system. So, you basically add a monofunctional reactant. Of course, this will end cap because it is monofunctional, and this is how you can also control the molecular weight. We talked about that before. So, this will limit the polymerization, and secondly, it will end cap the oligomers with functional groups that are capable of further reaction. All right. So, you can have cross linking, you can have chain extension example being this cyclic material, which you can also draw as this. It is a highly strained system. This is actually 5-norbornene. Okay. So, what you can do with this? You use this monofunctional material. So, you have an anhydride on this side and this is your norbornene unit. So, this is basically so this is 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. So, this is 5 norbornene 2, 3 dicarboxylic anhydride unit. Now, this molecule, if you include as a monofunctional reactant in your polymerization reaction between a dianhydride and a diamine. Let us say you are making an imide, polyimide. So, you are reacting a diamine with a dianhydride. Okay. We have talked about it in detail before. Along with these two reactants, you add this particular monofunctional reactant. Monofunctional, what is the function? It is monoanhydride. So, basically it will add at the end, it will not have another end to react further with the diamine like that. And at the end of this monofunctional unit, one side is your anhydride and another side of this norbornene unit for post polymerization modification. So, what you will get if you do the reaction? So, you take a dianhydride and a diamine and you take this monoanhydride, you add this also in this. So, in the polymerization, what we will get? We will obtain, or let us say we have an oligomer or a polymer, whatever. So, at the end of the polymer chain we will have this unit, because this anhydride has reacted with amine to produce an imide linkage, but at the end this will stay because this is a monofunctional molecule. So, let me draw this again here. So, your polymer chain at the end you have this. Now, if you heat this up around 270 to 320 degrees Celsius, if you heat this up you will get a thermoset product. How does that happen? This happens through what you call as Diels-Alder reaction. So, basically it is a pericyclic reaction. We will not go into the details of that class of reaction, but overall the ring opens up in a cyclic fashion, the electrons will move like this and this comes here and this comes here. So, what will happen is that it will heat up and this molecule will come out and it will be this, it will be cyclopentadiene, and what will be revealed on this side? Follow the arrows. On this side you have a maleimide end cap. So, basically it was a masked maleimide end cap unit to start with. So, you had a norbornene unit and you had a monofunctional monomer, in this case it is an anhydride that reacts with the amine, and then at the end of the polymer chain you will have this unit, an imide unit, because it is monofunctional. So, it will end cap and then this will open up by a retro-Diels-Alder reaction revealing the maleimide unit here, and now you know what is going to come next. This can be cross linked, and we have already talked about this kind of cross linking reactions. So, you can get your thermoset material. So, with this we will stop today, because one thing the time is up, and the second thing we are also done talking about polyimides. So, what we will do in the next class, we will start by talking about polyurethanes. The synthesis and the structure property relationship will again be at the heart of discussion. Till then, thank you and see you then.